Okay, so in section 6.1, we're going to be looking at the area of a region between two curves. And I think that this is, it kind of makes sense what we'll be doing here. So if I have these two curves here, and my blue curve is f of x, and my red curve is g of x, so we're just looking at a very general expression here that we don't really know the equations right now. And let's call this point right here, let's call this A, and let's call this B. And so what we'll be looking for here is we will be looking for the area between the curves. So like in this case, we would be looking for this area right here between the curves. So, you can think of a lot of the stuff that we'll be doing this with like design. So, like, let's say that we had this like really weird building that the front of the building was shaped like this and the back was like this, and here's our roof that we're looking at. We need to know the area of the roof for whatever drainage calculations or whatever we're looking at. Of course, this would be, in some sort of very weird artistic sort of building, but or you may have, something that you are designing that you need to know the area of for whatever particular reason. You might have an abnormally shaped plot of land or something that you need to find the area of, that you could use something like this to sort of approximate your area. But if we have this situation and we need to know the area between the curves, it's, I think, pretty intuitive what you would do here. If I take the integral from a to b of f of x dx, what does that give me? So whenever we take the integral from a to b of f of x, as far as the graph goes, what does that give you in terms of f of x there? Area under the curve. So like if I highlight that yellow here, that'd be the area all the way down to the x-axis underneath that blue curve. All right. So if I have that area, what could I do that would give me just the area between the curves? Subtract the g of x. So integral from a to b of g of x dx. So if we subtract that out, then we are looking at taking this part right here away, right, which just leaves us with the area between the two curves. So I could write it like this. Because they have the same limits, I also could write it like this, the integral from a to b of f of x minus g of x dx. So that is pretty much what we're going to be doing. Now, to do this, there is one key thing you must know, and that is which curve is the top curve and which curve is the bottom curve. Because if you don't know that and you subtract them backwards, you're not going to get the right sign. You'll still get the correct area in most cases, but it'll have the wrong sign. So like in this case, we know that this is the top curve and that red g of x is our bottom curve. Okay, so let's do an example. I'll let you copy that problem right there down. These on a calculator and see. Sometimes they might give us the graph, but on a lot of these, we're not going to be given the graph. So we've got a couple options of what we can do. I would like to graph this just so we can see what is happening here, but I'll show you after that what we could do so we wouldn't have to graph it. So in this case, if we do a sketch of what we've got here, we would have, well, let's see, 1, 2, 3. Okay, so y equals x squared plus 2. That is a parabola that has a y-intercept at 2. It opens upward, so you would go up 1 over 1 for this next point. Right here, we're only looking from x equals 0 to x equals 1, so we don't need very much of the graph. And that parabola would look like this here. And then we have y equals negative x. So y equals negative x, that is a line that has a slope of negative 1. So we end up with something that looks like this here. And we're only looking from x equals 0 to x equals 1. So we're cutting the graph off here. And we're looking for this area right here. So this one pretty clearly, whenever you graph it, you can see the quadratic is the graph that's on top. You can see that the linear is the graph that's on bottom. Let's say that we didn't want to have to graph this. What I could do is I could take a number somewhere between 0 and 1 and I could plug it in. So if I plug in 1/2 squared plus 2, that's going to give me 1/4 plus 2, so 2.25. Whereas if I plug in 1/2 to y equals negative x, I just get negative 1/2. 2.25 is clearly higher than negative 1/2. So that would let me know that this is my top function and this is my bottom. Okay, so for this problem, we're going to do the integral from 0 to 1 of our top function, which is x squared plus 2 dx. And then we're going to subtract the integral from 0 to 1 of negative x dx. And one thing, as I look through your test, that we really need to work on as we're getting closer and closer to the exam is you have to show every step on everything. So you need to show where you set up this interval. Now, I'm going to do the next step where I combine these. If you do one or the other, that's okay. But what I'm seeing is a lot of you might have a bunch of work and there's no integral symbol anywhere. You just, maybe in your head, you know it's going to be x squared plus 2x minus x, and you just start integrating from there, and you never write that down. And if you don't set up that integral, there's a good chance you're missing points on that free response. So whenever you do your free response, you want to label everything as you go. Because sometimes there's points for stuff that if you skip that step, you're not getting that point. So you got to watch out for that. So like you want to write out an integral before you start working this problem out. Now this one's a little bit weird because when I have, I'm going to highlight each section here. When I have this right here, it is the area right here, right? And then for this part, it is this area here. I really don't look like I should be subtracting there, right? It looks like I should add those together because you've got part of it above and part of it below. But you always want to do top minus bottom because when I integrate this part right here, it's going to give me a negative value. And then if I subtract a negative value, that's going to make it positive, which is like adding them together. So if you just always do top minus bottom, no matter whether it's above or below the x-axis, it will always take care of itself on that. So we are going to, I am going to put these together. So integral from 0 to 1 of x squared plus 2x, plus 2 plus x dx. And it would be okay maybe if you didn't write this, but wrote this instead. That would be fine, but you need to have an integral set up somewhere. And I just like this better if I put those in order. So x squared plus x plus 2 dx. Okay, so we are going to integrate this. We will get 1/3 x to the third plus 1/2 x squared plus 2x. And we are going to evaluate that from 0 to 1. And so we'll have 1/3 times 1 to the third plus 1/2 times 1 squared plus 2 times 1 minus 1/3 times 0 to the third plus 1/2 times 0 squared plus 2 times 0. But if you want to, go ahead and put just a 0 there. So really we've got 1/3 plus 1/2 plus 2. They usually give you fractions. They usually leave the answers just fractions here. So you're going to have 2 over 6 plus 3 over 6 plus 12 over 6. And so we will get 17 over 6 for our answer. So the area there is 17 over 6 square units. Okay. Questions? All right, let's look at our next one. This next one's going to be a little bit different because it does not give us our limits. Like the last one told us only to look from x equals 0 to x equals 1. This one does not give us our limits. So when I have a problem like this, if it's something that I can graph pretty easily, I like to graph it because it helps me see what I'm looking for. It also, in this case, is going to help me find what limits I need to look at. Whenever I have a more difficult equation, sometimes I'll try to just use different methods so I don't have to graph it. But I know what 2 minus x squared looks like pretty well, and I know what g of x equals x looks like pretty well. So if I graph 2 minus x squared, that is a parabola that has a y-intercept at 2. It's going to be upside down, so you're going to have this graph down 1 over 1, then we go down 4 over 2. And this is where that graphing from pre-cal comes in handy if you know how to graph those correctly. And so that's probably going to be far enough. So that is our quadratic. G of x equals x, that's just the line that has a slope of 1. And you'll see that it very nicely intersects that quadratic at 2 places perfectly on grid lines. If it's calculator inactive, it probably will. If it's calculator active, it may not. You may have to graph those and find that on your calculator. So we are looking for the area between those two curves, which is going to be this area right here. Now I can tell pretty easily here that these intersect right here at -2 and at +1. So I could just go on from the graph from what I've got. I'm going to show you guys how to find that. Let's say if it's something that you can't graph or just don't want to graph. So if I'm looking for the places where these cross, I'm looking for where their x values are the same. So I would just take the two equations and set them equal to each other. So 2 minus x squared. I meant y values there. Y values are the same. I guess x and y. So I just set the two equations equal to each other. That'll find your intersection point. So if I, oops, I've messed up. That is not squared right there. So if I move everything over here to the right-hand side, so my x squared will be positive, I'll have x squared plus x minus 2. And then that will factor into x plus 2, x minus 1. So that would give us x equals -2 and x equals +1, which I can already see from my graph. Okay, questions so far? All right, then we are going to set up our integral. So our integral is going to be the integral from -2 to +1. And it's going to be top equation minus the bottom equation. I think I'll probably do it all as one integral this time because eventually you're going to put them together to solve anyway. So you'll have 2 minus x squared minus x. And then let's put a dx over there on the end. And so from here, you're just solving this like you would solve any integral that's been given to you. So I'm going to go ahead and put this in order. So it would be -x squared minus x plus 2 dx. So when you integrate, you're going to get -1/3 x to the third minus 1/2 x squared plus 2x. And you've got -2 to 1. And so it's always top minus bottom, so you're going to have -1/3 times 1 to the third minus 1/2 times 1 squared plus 2 times 1 minus -1/3 times -2 to the third minus 1/2 times -2 squared plus 2 times -2. So here, I'm just going to leave this for right now. So let's see what we've got over here. So this is going to be, oh gosh, so many negatives. It's going to be -8 times -1/3, which is +8/3. But then you got the minus here, so it ends up being -8/3. Here you will have 4 times -1/2. That's going to give you a -2, but then it's going to become a +2 when you distribute that negative there. And then here you got -4, but it's going to become a +4. I really don't need these parentheses right here. And so we got 2, 2, and 4, so we've got 8. If I put my 1/3 together here, I've got -9/3 minus 1/2, but what is 9/3? 3 minus 1/2, so I've got 5 minus 1/2, which is going to give me 4.5 or 9/2. Questions? All right, we got a couple more we're going to do. I'll let you copy this next one down. All right, so you'll have a few like this on your homework where you're not actually being asked to solve the problem at all. You're asked to sketch a graph whose area can be found by the equation here. So, so for this graph, this looks like our top function should be negative 2x plus 5. The bottom function should be x squared minus 3. And we're only evaluating from 0 to 2. So we only need to look between x equals 0 and x equals 2. The graphs may continue on after that, but we're only concerned with that part here. So sometimes it's a little hard to tell like how tall your y-axis needs to be. But if I plug in 0 here, I'd get 5. If I plug in 0 here, I'd get negative 3. If I plug in 2 here, I'd get 1. If I plug in 2 here, I'd get 1 also. So it looks like 5 and negative 3 are probably pretty safe bets. So if I go from like negative 5 to 5 on my y-axis, that should be pretty good. And the x-axis, we really only need to go from 0 to 2 because that is all that we're integrating. So then you're just going to graph your two equations that you've got here. So you've got negative 2x plus 5. That is a line that has a y-intercept of 5 and a slope of negative 2. So you're going to go down 2 to the right 1, down 2 to the right 1, and draw in that line. And then you've got x squared minus 3. So that is a quadratic that has a y-intercept at negative 3. And so this point would be up 1 over 1, and then up 4 over 2. They're going to cross right there. Like this. And then your limits are from 0, so x equals 0, to x equals 2. So even if they didn't cross perfectly right there, we would stop at 2. So our region would be this region here. Any questions on those? All right, here's our last one. Okay, let me try again. Make it a little bit prettier. All right, so if we graph this, the highest sine or cosine can be as 1, and the lowest it can be is negative 1. And then 2 pi's when it starts repeating. So what's half of 2 pi? Or well, let's see. It would be pi, or what's a quarter of 2 pi? Pi over 2. So right here I'd label that pi over 2, and then I'd have pi, and I'd have 3 pi over 2, and then 2 pi. So if you just use your unit circle values, or hopefully you might remember what sine looks like. Sine begins at the x-axis. It goes to a maximum point, midline, minimum point, midline. So sine is going to look something like this. And then if we graph cosine, cosine begins at a maximum point and goes to the midline, minimum point, midline, maximum point. So cosine is going to look like this. Now, we can definitely see that they intersected, but they did not intersect at a beautiful, lovely place where I can just look on the graph and tell exactly where that's at, based on what I've graphed so far. So for this one, you pretty much have to say sine of x equals cosine of x and solve that. And there's really not so much a way to solve that except for thinking, there are a few, but the best way to solve this is just to think about your unit circle. Where does sine of x equal cosine of x?
Square root of 2 over 2, negative 3.
Yes, and what is the not pi over 3, pi over 4. So pi over 4. So we're right there on the unit circle. Right there is pi over 4. Where else? 3 pi over 4 is here. And so at 3 pi over 4, one of those is negative and one's positive. It's not 7 pi over 4, because that's over here. This is 5 pi over 4. So x could equal pi over 4 or 5 pi over 4. Or if we wanted to keep going around the unit circle infinitely, we could find all the next intersections as well. But we only care about one section. So from pi over 4 to 5 pi over 4 is where we're going to look. And for our graph, which function is the top function for this, sine or cosine? Sine is our top function in this section. Now, like, let's say that I wanted to go from 5 pi over 4 to 9 pi over 4 for some reason that I wanted to punish myself with that, then cosine would be on top there because it's going to switch back and forth. But if the section we're looking at, sine is on top. So we're going to integrate from pi over 4 to 5 pi over 4. And we're going to say sine of x minus cosine of x. And we'll put the dx over here on the end. Make sure you put that dx there on the end because I am worried that they are going to count off your setup points if you don't have it. Alright, so we are going to integrate this. When we integrate this, integral of sine x is negative cosine x, and the integral of cosine x is sine x. And we're going to evaluate that from pi over 4 to 5 pi over 4. So we're going to end up with negative cosine of 5 pi over 4 minus sine of 5 pi over 4 minus negative cosine of pi over 2 minus sine of, pi over 4, not 2, and pi over 4 here. So this negative right here, if we distribute that, it's going to make both of these positive here, so positive and positive. So we've got negative, the cosine of 5 pi over 4 is negative root 2 over 2, and the sine of 5 pi over 4 is negative root 2 over 2, plus cosine of pi over 4 is root 2 over 2, and sine of 5 pi over 4 is root 2 over 2. And so right here, these double negatives are going to cancel out. Right? So we really just have root 2 over 2 4 times. So we've got 4 times root 2 over 2, which is going to be 2 times the square root of 2. So the area of every little section there would be 2 root 2. Okay, questions? All right. This is not right. It's from the old book. Still messing that up. Okay. So your assignments, you got about 15 minutes to get started on it, is going to be page 414. And I want you guys to do 1 through 6, 7, 8, and then 19 through 25 odd. Now, that sounds like a lot, but on 1 through 6, you're just setting up. So on 1 through 6, just set up the integral, do not solve it. So it should not take that long to do that part. 7 and 8, these are the ones where you're going to sketch the graph. And then 19 through 25 is where you actually find the